The derivative doesn't have to be defined at every point. In this video, we'll give some examples of how a derivative can fail to exist. So, rule 1, as it were, for a derivative to exist at a value, f of x must be continuous at that value. We are not going to formally prove this, although a demonstration does exist in the textbook, and I believe in your notes. Let's just remind ourselves that f prime of x sub 0 is a rate of change at x sub 0. And if a function is discontinuous at x sub 0, this corresponds to an infinitely fast change. It goes instantly from here to here. So informally, the reason we need continuity is because if we don't have continuity, the function is changing infinitely quickly. However, continuity isn't enough. A function can be continuous at a point, but still not have a derivative at that value. And that can be for a few reasons. The first reason is this. It's possible that a function is continuous at a point, but is still changing infinitely quickly, as it were. How can that be? The easiest way to understand this is the following statement. For f prime of x sub 0 to exist, the tangent line must not be vertical. So remember, that the closer to being vertical a line is, the larger its slope is in absolute value. So you could informally think of a vertical line as having an infinite slope. And since the slope of a tangent line is the rate of change, you can see that having a vertical tangent line ties into this idea that the derivative can't exist if the function is changing so quickly that its rate of change is infinity. And there are perfectly nice functions that have this problem. F of x equals 1 divided equals x to the 1/3 power, I mean. Let's get a graph of this up on Desmos. Here's f of x equals x to the 1/3 power, and you see this graph is increasing awfully fast here around the origin. In particular, if we zoom in on the origin, this function is increasing so quickly that it looks as if it's just a vertical line. Well, in fact, x equals 0 is the tangent line at 0. And vertical lines don't have slopes. So if the derivative is the slope of a tangent line and the tangent line doesn't have a slope, then the derivative doesn't exist. Another way that a derivative could fail to exist is a little harder to summarize the way we summarized the previous two cases. But if I were going to try, I'd say that for the derivative at x sub 0 to exist, x sub 0 must not be the location of a sharp corner. And the classic example of a function whose derivative fails to, at a point, fails to exist because of this reason is the absolute value of x. The absolute value of x, let me get rid of all of this, The absolute value of x looks like that. It's continuous everywhere. It doesn't have any vertical tangent lines. But the derivative at that sharp corner doesn't exist. Why is that? Let's try to figure this out. Suppose we have some other curve without a sharp corner, and we're interested in the derivative at the point. The derivative is the slope of the tangent line, and we introduced that in the following way. Suppose this curve is a road, and you're driving along this curve, and you reach this point, and your steering fails, and suddenly you're stuck going in a straight line. What line in particular will you go along? You'll go along the tangent line. That's not the best art, but does it matter which direction you're traveling in? No, not really. If you're traveling in this direction and your steering wheel fails, you'll drive along the tangent line like that. If you're traveling in this direction and your steering locks, you'll travel along the tangent line like that. So you have a single tangent line. Now compare the absolute value of x, and suppose that your steering fails at this corner. What direction will you drive in? There's no longer a single answer to that. If you're driving in this direction, you hit this corner and your steering wheel fails, you'll drive along in that direction. On the other hand, if you're coming from this direction, you hit this corner, your steering fails, you'll go in that direction. So there's no single tangent line that tells you the direction of the curve at this point. You can go along different lines depending on which direction you approach this point from. And obviously, this tangent and this tangent do not have the same slope. So asking for the slope of the tangent at that point doesn't make any sense. So what we've seen are the main ways that a function would not have a derivative at a point in spite of being defined at that point. One take-home message from this is that functions, or at least certainly the standard functions we're used to working with, almost always do have derivatives. I mean, go back to these examples. This function isn't differentiable here, but it's differentiable everywhere else. X to the 1/3 isn't differentiable here, but it's differentiable everywhere else. The absolute value isn't differentiable here, but it's differentiable everywhere else. So these are kind of special cases.